Welcome on my talk. Today you will hear about continuations and this real world of continuations. What I mean by this world. A long time ago, actually not long time ago, a few years back, I was working in this company. This was my first job, and I was a Perl programmer. So you may think right now, Perl, what I'm doing here? Wait a second. Perl is not that bad, and it will be not the only language I will be talking about today. So in this company was this Perl program. I was recruited as a software tester, but later I was turned into a programmer because on the first day of during the interview, I told my boss that I know Perl, and by knowing Perl I meant, yes, I used Linux and some Perl scripts copied and pasted into the command line. So when he asked if I knew Perl, what would you say? You are a student, fourth year, and do you know that? Yeah, sure. So I became a Perl programmer and also JavaScript programmer because, as you may know, Perl is not a front-end development language, and this was a web application. So Perl and JavaScript were two languages we were using. So I became Perl JavaScript developer. But there was this but. This project had a main developer who was very, very avid user of Lisp. And these three languages kind of formed my programming background from the beginning of my professional career. So, as you may know, Lisp is the language with many parentheses, and there will be some parentheses today, so don't be scared, don't run away. It's just Perl, just JavaScript, just Lisp. Okay, stay, for a while at least, please. So, not long time ago, in a galaxy not far away, I was in this situation, because my colleague said, you have this book, this is a Bible of Lisp, read it. You will be floating around through the parentheses and other constructs you will do by yourself. You will create whole galaxies, whole universes. And I was thinking, yeah, that should be the language the gods wrote the universe in. And last slide is my favorite because it's XKCD. Do you know this comics? Yeah, so it perfectly describes what I was feeling back then. Because, yeah, it was just a Perl, but written in a Lisp way. So now you may think, oh, it's weird, and it was weird. So let's see. Yep.
Which book it was?
Sorry?
Which book it was?
Structure and interpretation of computer. Yeah. So. Okay. I didn't mention it. Yeah, sure. So, our web applications, because the senior developer had this power of creating assumptions about it, and directions in which we have to develop these applications, there were a few. For example, the functional is the right way. Remember, this was Perl and JavaScript, so no purely functional languages, but anyway, functional style is the right way to do stuff, every stuff, basically. So, because functional is okay, side effects are bad, you know that, yeah? And what's more? Yeah, naming is hard. So, my colleague was very, very strict on this. If you don't have to name something, just don't name it. So if you use some function and you use it one time, just inline it. So, okay, so you are building the image, yeah? So besides naming, there is a thing about variables and return. They are bad. This was our assumption. I mean, if you had to return something, it was kind of smell. Yeah? Now you may wonder how can you deal with things without return? Because without variables, you may know Scala, for example, varval, the difference, but without return. Yeah, actually, it was a concept, I would say, taken from Lisp scheme, which I will describe later. So, and because returns are bad and returns are passé, so we had to use some kind of hack to pass this return Yeah, so we used continuation passing style, CPS for short, for controlling program flow. I mean, programming whole programs, our web applications. So to do that, we had some utility. We used some utilities. How many of you know what does car, CUDA, and cons mean? Yeah? Oh, yeah, this audience is nice. But for those who don't, anyone can explain in 2 words? What are the synonyms for car and CUDA? Maybe well known? First rest, head, tail. Yes, exactly. So these are basically words invented in 1950s actually for the Lisp programming language in the beginning of the computer programming. On the first IBM 701, I think, computer, there was this 36-bit word which had first 15 bits which were contents of address register and the next 15 bits which are contents of decrement register. So hence the name. Yeah? And the cons, what's the cons? Construct, yeah. So how does construct work? We will see in a while. And another utilities we used, map filter reduce. How many of you know that? Yeah, if you don't and you're here, you should just, you know. Okay. And as I mentioned, continuation passing style for a program flow and some kind of fancy stuff which will be described if we had time, if we will have time for this. Y Combinator? Anyone? Okay, not so bad, not so bad. Nice. So, Lisp 101, for those who don't know Lisp. Lisp, basically, Lisp 101 in 5 minutes, maybe a minute. You have to know one thing. This is the syntax. Yeah? Actually, this is very, very important construct because this is actually nil, an idiom. Many Lisp, different Lisp dialects have nil. Okay, this is nil. That's all. And this is actually a singly linked list in the some kind of Lisp dialect. Let's talk about, for example, scheme, which is 1, 2, 3, because we construct list which consists of atom 1 and then list constructed from atom list. Oh no! From this side. This is a list which is constructed from the nil node and 3, which is constructed with a previous node of 2 and previous node of 1. So basically, this is something like that. Because, you know, Lisp has this kind of macros. You know what macros are? They basically, the universe you saw created by the guy on the second slide was using macros and something like some stuff like this. So this can be notated in the Lisp notation like this. This is the same as this. So 1, 2, 3 nil, it's list of 1, 2, 3. And you can see this as some kind of a, for example, unbalanced binary tree, which has nodes 1 and 2 and 3, and nil on the right side. So basically, we just came to the easiest notations for the 3-element Lisp, which is 1, 2, 3 in the parentheses. And if you do the cons on this list, it will be something like this. Yeah, easy. So Lisp 101, you're good. You can do more Lisp stuff. Read about it if you haven't already. So back to our web application. We used Perl. So Perl is not a Lisp. Yeah. So how did we do this? We programmed it by ourselves. So we had this cons subroutine, car subroutine, and CUDA subroutine, which basically this is how many of you does know a Perl syntax? Oh, few people? No, maybe. So for those who don't, this is a Perl way of passing of argument signature, because Perl doesn't have arguments in the signature of subroutine here. You can just access the argument array, which is denoted by @_, and extract it, assign it to some kind of variables in the parentheses, which force the list context. Okay, so Perl 101 wouldn't be 5 minutes, so I won't be, deep in the details. But basically, you may imagine if this is a cons, parentheses first rest, and these are arguments, and just return an array reference created by the first element and dereferencing to a list the reference to the array, which is rest. Easy, easy peasy. Yeah, this is Perl easy. So car is actually kind of similar because we use the reference to the list, scalar reference to the list LST variable, which is an array. And because this is evaluated in the list context, we can have this first element of this list and the rest, like tail, you know, and just return the first element. And the same, this is the CUDR, but we return the reference to the array rest. So easy, yeah? But you came here for the continuations. What are continuations? Who can tell me the difference between these three and in 3 words? Closures, callbacks, continuations. What are closures? Yeah?
Yeah, I can tell you the first two at least. So closures are a construct where you capture variables from the outer scope wherever you define it. So normally this is a function that captures a variable outside the function declaration.
Yes, so I will say this again to the microphone. Closure is a function which captures some kind of local state. Yep, okay. Callbacks? Anyone?
Callbacks, I think they're just simply functions that are passed as arguments for that function.
Yes.
That's the first one.
Sorry?
Sorry.
Yes, so callbacks are basically functions which are passed as an arguments. You have to have language which allows that. But yeah. And continuations? Simple explanation, please, because we will be... Sorry?
The tail call optimization,
yeah? The simplest way would be by example, like when you have a
okay.
loop, then break or return or exit or die in Perl or I don't know, continue. These are examples of continuations. Or goto is a comment, or throw.
Yeah, so we'll be deep into that. Yes, sorry. Yeah.
If you have a function, you can, instead of returning from that, you can, let's say, provide another function that if you call once it has its result.
So basically, you guys just provided 2 correct definitions for continuations, but in different definitions in the sense of continuations can be, as you said, callbacks which are passed and executed as a last step of the current subroutine's current function, and hence can emulate return, or continuations can be some kind of control flow structures. Yeah, so listen. Yeah, so first things first. Quick implementation of map, nothing fancy here, but fancy language, JavaScript. This is a example implementation of map. What is important is the function here, which is executed here. This is a callback. This is not a continuation. Yeah? Agree? Yeah. So basically, this is the usage of this, and this could be a kind of native use of the same. In the JavaScript, newer browsers support that. Internet Explorer 8 does not. Okay. So this is the same in the Perl definition, usage, and in the plain Perl you have actually the map, which is much more terse and concise. It's here. It's the same, but it's Perl style, code wolf. But it's quite readable. Map, the underscore, if you know Scala, and this underscore concept is the same. It's a kind of current variable. Just takes squares from this list. It's fine. Looks nice? Yeah, actually this is a correct answer because we did not use this construct. It tends to be nice, but if you have this longer body of the block of the function here, it tends to be not very readable. So yeah,
it looks backwards.
Sorry?
It looks backwards. You put the data at the end and not at the front. It's actually the right hand. I disagree.
Not enough, because this is Perl, you don't have to have parentheses. So, and just example of for each, and usage, not very important. What would you have to, what do we have to do if we want to have a continuation here? Because this is not continuation, remember, this is some kind of function which is a callback. If we have some kind of continuation, we have to, for example, add it. Because this is some kind of function which will be executed, as we said, as a last step of this function. And this now is a continuation in the sense of, as you mentioned before.
So with the unit parameter, right?
Sorry?
With the unit type parameter. So.
Yeah, so basically, in Perl there is no concept of unit type, but yeah.
Just because of the for each.
Oh, yeah, so, sure.
So what's the difference between a callback and a continuation?
What's the difference? As I said before, callback is just a function which can be passed as an argument, generally, which will be invoked later. And continuation is a function which will be passed and invoked as a last statement. It may be even more readable in the example in a few slides, okay? Okay, so we'll go to this.
So every continuation is a callback?
No, because yes.
You get the lazy evaluation with continuation. That's the difference.
Yeah, but actually continuation does not have to be a function. We will go through that, okay? So remember, this is easy. About continuations, we will go there, okay? They will be there. So, addressing your question about continuations, this is not the code which uses continuations. This is just a code which is a kind of reads line by line. Yeah, standard imperative code which does capitalized guys exactly blah blah blah. Yeah, easy peasy. But the flow of the program is actually does this, returns to the main program, does this, because it reads right like this, And if we use continuation passing style with the continuation, which I will be showing right now, this will be something like this. We have the same logic, but used with continuation. We pass additional argument, a function. Here this is a callback, but this is executed with the result. We don't return the result. We just invoke the continuation with the result as its argument. So now can you see the basic difference? Continuation can be callback can be continuation, but it's not hard, strict, So basically, as you can see, the program flow looks like this. Now, we have main program, which does the concat, which invokes some kind of continuation, which is our function capitalize and print, which does capitalize, and some other function, print, and does the console log. So the program flow is, in the sense of, for example, debugging, can be easier to debug, because you have this whole flow available right from the beginning, actually. So, but the downside is what? You have to do this, yep?
And you may get stack overflows.
Yeah, you can get stack overflow.
And it may be harder to debug because you don't have the intermediate state available.
Yeah, this could be true. So, listen. Because, as I said, continuation does not return, just invoke another function. We have this possible stack overflow. Yeah, we have this nice looking flow, but we don't return. Yeah, what's the hint? We have this callback, let's say callback, and invoke it instead returning. Yeah, it's clear. So it's continuation passing style. To be very, 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 very clear here, this is not a continuation passing style. This is an identity function without a continuation passing style. This is identity function with a continuation passing style. Yep, clear. So, in the real world, we use continuation passing style actually. For example, using Ajax calls. This is jQuery in JavaScript. If you know JavaScript, you probably know the jQuery library. And we just invoke do the post request to this address, and when we have the data back, we have this callback and do some stuff. Yeah, so basically, when you do JavaScript, you have this whole bunch of callbacks you can be invoking because of an asynchronous model. Yeah, the same is in Node.js. So, for example, this is the function readFile, which obviously reads file and does something when when there is error or data. So, if there is an error, throw an error, else console log data. But now we have this problem because if we want to use continuation passing style, we don't have to return, or we must not return, and we must not, for example, throw, because it does not fit in the flow which we saw on the earlier slide. So what will we do? We just pass another callback which can be invoked. For example, assume that we have this function readFile CPS, and instead we using one callback which has two arguments, error and data. We have two callbacks, error callback and just an ordinary callback. Yeah, cool. So two continuations instead of one. Yeah, that's okay, because if we have this error, we will go there, and if we don't, we go there, and the program continues. And actually, this is kind of neat because error callback can be anything. I mean, you have this function which reads file, and it's not coupled to the error handling. I mean, if you throw, it is not coupled too, but it is the flow is nice, and you can pass an error callback, for example, to die, the program dies or exits, or just I don't know, write some alert in the browser. Yeah, so it's your choice.
There you have very little state for resolving errors.
Sorry?
You cannot pass the state when you read into the error callbacks. That's a problem with that. You have, in the error callback, you don't have access to the data about what kind of error you were when you in the state of the passing function.
Yeah, so basically...
that's a problem.
Here, the implementation of readFile CPS provides some context in this argument. This is the only way, basically. So you have to write things differently. I mean, this implementation, if you want to access some state of the error and state of the program during the error, you actually would have to pass some kind of state here, error state, actually, yeah? So, continuations, and as it grows, we can just write like this. This is Pythagorean. Okay, so you have this triangle with Pythagoras
theorem.
Yeah, theorem. Yeah, thanks. And using continuation passing style, it's weird. Yeah, because we can do this just sequentially squaring and adding the results, and we will have the same. So this is even worse than the first example, and you may imagine. Remember, our web application, what I said in the first slide, don't name things if you don't have to. So the consequence is, basically, we could just have this function named and put here, and it will be much more easy to read. But in our application, we actually didn't do this, because if something is used just once, for example, like multiply or add, just inline it. So you may now imagine how this is looking, yeah, this pyramid, and also Stack Overflow possibility. And this is a problem. This is a problem. Obviously, this is a problem in the language like Perl or JavaScript, which actually does have Stack and can have Stack Overflow, and does not actually have tail recursion, tail call optimization, I mean. Because, why? This for tail recursion, tail call optimization, no, these three. What is the difference between tail recursion, tail call optimization? Can you tell me? Basically, anyone? Yeah?
Tail recursion is a special case of tail call optimization. No.
Not really. Tail recursion is just the fact that you can...
You're calling yourself at the tail.
Yeah.
You have a tail call optimization, but just a special case of it.
The special case of tail call, but without an optimization part, yeah? The special case of tail call, because this is not a tail recursive implementation of a factorial function, because, why? Anyone?
Multiplication is at the end.
Multiplication is the last thing.
Yeah, maybe you don't see this if you don't do much functional stuff, but for example, if we were using Lisp, it would be much more readable here, yeah, because this will be the last. I mean, the most.
But that's not tail recursion.
So this is tail recursion, tail recursive version, yeah. So tail recursion is the thing here. You have tail fact function, which is the last thing called in itself. So tail call is basically the most simpler case when you just have this, let's say, continuation or callback, which is called in the tail position. Yeah, easy peasy. And the tail call optimization is just a trick of a compiler or interpreter or whatever, which does prevent you actually from having stack overflow. Yeah. So instead of doing this pyramid of do messages called this kind of stack growing here, compiler can automatically translate this code to iterative version, because this does not grow here. Yeah, you can see this. It's quite easy. But as I said, tail call optimization is the trick of a compiler, so you don't have to worry about this. If you write the right thing in the Lisp, for example, the compiler will do this for you, and you will not have the stack overflow. But in Perl, for example, how do you do this? You can manually call the tail. You can manually do the tail call. Yeah, but you have to use this module, and what it does, it actually takes the current subroutine and passes. Go back. For example, here, if we used tail in Perl here manually, this will be the current stack of this function will be replaced with these arguments. So this is kind of hack, because the stack does not grow because we replace the arguments which were the current function invocation. If we see the stack of the last execution of this function in Perl, this would be just 0, 6 and no sign of these arguments. So it's kind of hack, yeah? It's not a kind of hack, because this is a module. The module which does beautify the way of implementing tail call optimization, using tail call optimization in Perl, because basically what it does this. As I said, just assign to the arguments list something and invoke it by going to the definition of the current function of this function. If it's a tail call position, just go to the current function definition with another arguments. But actually, it does not cheat. It does do what it does. Yeah, because tail call optimization is the manipulating of the stack and state, and you may just end up with a not readable stack trace. Yeah, it can be a problem, but you don't have stack overflow.
Okay, one question. Because
yep.
I think this applies to tail recursive situations. And
yeah, but actually you can invoke use the tail in Perl, for example. Here, you can invoke a function with this tail call, which is not in a tail position. Yeah. Basically, in this example, this would be useful, yeah?
Yeah, sure. But what about the continuation passing style in general?
Can you repeat?
Because this applies only to the tail recursive situation, yes?
Yep.
And when you have this continuation passing style
situation, I think that answer is because you are passing just a function. It's just another argument to pass to the tail called function. It's not a difference. So, as you can see, goto, it's not lying, Perl is not lying you. It just goes to the function with these arguments. So goto is bad. Is it? Actually? Yeah, no. It's not that bad because it's not like you are using and writing unreadable code, but compiler interpreter does it for you. So it does not eat you. If you trust your compiler or interpreter, it does not eat you. So continuations. Actually, I lied to you. These are not. There is not the only meaning of the continuations in the sense of continuation passing style. It's not an exact continuation, yeah, as you said, because what are continuations? In fact, they are not even functions, because continuations are abstract representations of the program state, as reads from Wikipedia from the page of continuations. You may wonder, what? So, go back to the Lisp part, Lisp 101, and this universe creating thing. Because Lisp can be just this parenthesis thing, and no constructs like, for example, I don't know, if, or loop, or throwing an exceptions or catching. Continuations are this abstract representation of the concept of, can be abstract representation of concept of, for example, if or throw, or even return. Remember, we didn't use return. Why? Because in the Lisp, in the our protagonist language, it just basically didn't have to exist. So continuations, the real continuations. I mean by real, there is this confusion, yeah, because continuation appears here as in continuation passing style. Yeah, we talked about this. And, for example, continuation as an abstract representation of a program state can be, for example, first-class citizen in language, like this is in Scheme. For example, what's interesting, for example, Ruby has these first-class continuations, but they are not actually functions. They are objects. So continuation does not have to be a function. It's a representation of state. And by representation of state, we mean that, for example, we can have the whole stack trace of the current function which is invoked, and we can just grab it and save it for later. Yeah. So basically, first-class continuations allows us to recreate program state. Yeah, because we are now here in the function with these arguments and this stack. In the functional world, if we just save it and invoke later, it should not be the different result, yeah? So, why not? So, let me tell you an example. You are in your home, it's evening and you're hungry, yeah? So you come to the refrigerator and you just have the continuation, save it, and to the pocket, yeah? So you have a continuation, yeah? We are hungry, remember. We open the door, we have this, for example, butter, we take bread, do ourselves a sandwich, have some, for example, cheese, and, yep, so we just made ourselves a sandwich, and now we take our continuation, pick. We are standing in front of the refrigerator with a sandwich in the hand, and we are hungry, so we just eat it. Yeah, so we had this continuation, we saved our state of stack, we are hungry, standing in front of the refrigerator, but some variables changed. I mean, some state changed, not variables, sorry. Sorry. Some state changed. We have this sandwich, yeah? So, continuations. First-class citizens, for example, in Lisp, have this function, this construct, called as current continuations, abbreviated with call_cc, which is a control operator, and actually it could be the only control operator of the language. You don't have to have returns, ifs, throws, because you can implement it by yourself just using the call_cc. Yeah. So let's do some Lisp. It's maybe not 101, but we'll try. Okay. So I think this is from Wikipedia, and what we are doing here, we are using the call_cc here. Let's take the first line. We just define the function. We just define the continuation just instantiate to the false, to false. It's nothing right here. And then we define the test function, which defines the local variable I. And the magic happens here, yeah? So we have our continuation. We put it in the pocket, remember? What it does, it sets the continuation, defined here, to some kind of current continuation. The argument is a current continuation, yeah? So K. And what it does, it just increments I and returns. Okay? Let's see the usage of this. So we have test. Test is here, remember? This function with the call CC inside. Because we assigned, by using test, we assigned the current continuation to some K, and this now has some state. If we invoke test, it returns 1. If we invoke this once, it returns 2. Twice, it returns 3. But the magic is now happening here. We just have this the continuation, which we use here, assign it to another variable here, and just reset the continuation. We're just going back to in time. Yeah. So because we are going back in time, what's the first value of I? It's 0, and it returns it by it returns its value by incremented by 1. So because we reset this continuation, it prints 1 and then 2. But if we have this another continuation reference to the previous continuation, it will print next value of 3, which is 4, because it's the saved state of this first continuation. Yeah? You may see the picture now, don't you? Yeah? So basically you may just think, yeah, I know this. I mean, is this some kind of generator like in Python? You use Python? Anyone? Yeah, so is this some kind of generator? Yes, actually, continuation is an abstract representation of the programs of the control program state. So generators can be implemented as implementation of some kind of continuation. Yeah, and it's true. For example, this is another maybe more practical, slightly more practical example. We want to define some kind of new function which will just display the inverse of a positive number. So if we have 2, it will display a half, 1/2. So it's inversion. Yeah. So we define this function, and of course we have the problem: what if we have 0? Because you cannot divide by 0 by anything by 0. Yeah. So if we have 0, we just don't divide, just return false. But you see, this is a problem. If you have the list of 1, 0, 2, the result of this would be 1, false, and 1.5. Because you don't terminate, you just go with the whole 3-element list and do the math on this. So we have to do some kind of check, and after the using map slash function, you have to check if any of elements is actually false, to be sure that the result is only consisted of valid values. And you can do this by using continuation. So instead of here just returning 0, we use our continuation here. Yeah. We put it in our pocket and just use it. So instead of the result of this being 1 false, 1.5, it is just false. Why? Because if this goes here to this branch of this if, it just invokes the continuation which just returns. And actually what we did here, we just implemented some kind of exception throwing, for example, here. Yeah? Because the continuation here serves us a purpose of an exception. So yeah, basically continuations are not only meant as in continuation passing style as in, for example, jQuery Ajax call, but actually continuations are much more abstract concept which can be used, for example, in Lisp to implement control structures, any control structure. And it's the beauty of Lisp, as I told you a few times, that you can create whole universe by yourself, which is nice, but also very, very, very risky. Yeah. So, but it's beautiful, isn't it? Called CC. So if you have not ever used Lisp or any kind of Lisp, I mean Scheme, Racket, whatever, maybe after this talk you will just sit and read something about this because it's kind of nice. Yeah. Without having any kind of language construct, we can actually implement return, if, throw, whatever, using the current continuation. So I don't have any time to talk about Y Combinator. Maybe you will read something about this. Basically, it's the way of defining a recursive function without naming it. Because, as I said, we didn't name things. If you have the recursion, you have to have, for example, name of a function or the function definition first and invoke it within itself. But with Y Combinator, you can do this anonymous recursive call, for example. Sorry, I don't have time for this, so maybe next time. Any questions? Yep.
How to implement? Because you said that it is possible to implement if using call CC, and the question is how to do that.
Yeah. Can we? I can answer you after this talk, okay? Because it's not that quick response. So basically, let me say just one thing about the Y Combinator. Here is the link to the very, very nice explanation of Y Combinator using Python. So it's very it's not Lisp, not scary. Yeah. So if you want, just check it. Yeah. So thank you.
Any questions?